Alrighty, we're looking at 8.6, comparing linear, exponential, and quadratic functions. So here we're going to be, like it says, we're going to be looking at different data or different functions, and we're going to be able to classify them and analyze them and look at the differences between the linear, exponential, and quadratic functions. So first off, we have this statement here that the average rate of change is the slope of a line through 2 points of a graph. So right here we want to say we're going to graph y equals x squared minus 4, and then it's going to ask what is the average rate of change from x equals 0 to x equals 2. So we're just going to draw a small graph here. And starting off, that -4 tells us to go down 4 spots. 1, 2, 3, 4. We got a dot down there. Then we use the numbers 1 and 4 to go up 1 over 1. In both directions, and the 4 tells us to go up 4 and over 2 in both directions. So we have our quadratic right there. Now they say they want us to look at x equals 0 to x equals 2, so that's going to be going from that point to that point. And right here we have it graphed, and we can see it nicely. We have the point 0, -4, and then the point 2, 0. Now we're able to just pick those out of our graph here. If we could not, then we would make a t-chart, right? You know, like an XY chart, and we plug in 0 to get -4, and we plug in 2 to get 0. Okay, so like on the homework, it might ask you this, and you might not have to graph on the homework, but you can still make your little t-chart. You can just plug in. Now, so say we got this quadratic, and it's modeling something. Who knows what's it modeling? But you want to look at, well, how fast did it change from 0 to 2? So that's going to be finding the average slope. So we're going to say our slope formula M is y2 minus y1 over x2 minus x1. And this is going to be like my x1, y1, x2, y2. So our slope is going to be 2 minus 0 over 0 minus -4. The numerator simplifies to just be a 2. The denominator simplifies to be, you know what, did I just plug that in wrong? Oops, I did. Look at that. I accidentally put the x's in the y spot, didn't I? The y's go on top, right? So I'm going to say 0 minus -4. There we go. There we go. That's better. Over, all right, hold on now. 0 minus -4 over 2 minus 0. Yeah, that's x2 minus x1. There we go. Finally. The double negative there turns into a positive 4, and then 2 minus 0 gives us a 2. 4 halves is 2. So our average slope is 2. Right, and it can be sometimes difficult to talk about a quadratic right here in the beginning, or anywhere really on it, because it's always changing. But we can look at the average slope there, or the average rate of change, and it's 2, and that can help us kind of see what's happening maybe in a little more simplistic way. So there we go. Our answer is 2. Now we're going to plot the points, and then we're going to tell whether the points appear to represent a linear, exponential, or quadratic function. And then after we do that, we're going to try to write a function that models the data. So starting off, let's draw a rough little sketch here. It doesn't have to be very good. -2, -1, there's our first dot. -1, 0. 1, 2. 2, 3. And then 0, 1. Well, from my picture, I can tell right away, this is going to be a straight line. All right, we're looking at a line like that there. So it appears to represent linear. And then we want to write a function that represents that data, and we can actually pull directly from this. I'm going to think about y equals mx plus b, right? The slope-intercept form that we know and love. Our y-intercept, it looks like it's going to be at 1, and my slope also looks like it's going to be 1. So I'm going to have 1x plus 1. That's y equals 1x plus 1. Now I'm going to plug in a couple points just to make sure that this is right. Let's draw this kind of nicely with function notation. F of x equals x plus 1. Plugging in a few points, -2 plus 1 is -1. Negative 1 plus 0, or excuse me, negative 1 plus 1 gives me 0. 1 plus 1 is 2. 2 plus 1 is 3. 0 plus 1 is 1. So yeah, it looks like that one is looking good. This guy is linear. Linear. All right, there's 25. 26, we're going to plot the points, and we're going to tell whether the points appear to represent a linear, exponential, or quadratic function. Then we're going to write a function that models the data, just like last time. So I'm going to look at plotting these points. Negative 1.2 is going to be somewhere in that region. 0, 1, 1, 5, 1, 2, 3, 4, 5. And I'm not going to plot the rest of them because those are going to be way off it. We can see that it's going to be exponential there, isn't it? All right, if I can draw that curve in there a little bit. It's going to look pretty exponential there. Our exponential curves are normally written y equals ab to the x, where a is the y-intercept and b is the rate of growth. Our y-intercept is 1, and then the number that we're multiplying by each time looks like it's 5, right? From 1 to 5, you multiply by 5. 5 times 5 is 25, times 5 is 125. So it's going to be 5 to the x. So writing this kind of nicely with function notation, f of x equals 5 to the x. And if we want to check ourselves, we can plug in a few points. 5 to the 0 is 1. 5 to the 1 is 5. 5 squared is 25. 5 cubed is 125. I think that's going to be okay. 27. Oop, did I ever say that he's exponential? Nope, I didn't. I'm just going to circle that right there to say that he's exponential. Plot the points. Tell whether the points appear to represent linear, exponential, or quadratic. And then we're going to write a function. Now, since we've already had linear and exponential, I'm thinking this guy's going to be quadratic. Let's go ahead and graph this. Negative 3, 2. Negative 2, 4.5. Somewhere in that region. Negative 1, 8. 5, 6, 7, 8. 0. Oh, did I write that wrong? I did, didn't I? Oops. There. 12.5 would be somewhere up in that region. And then 118 is somewhere there. Well, I can't tell if that's... Maybe my graph's just bad, but that looks kind of like linear, doesn't it? Well, when you're struggling to know, you can always use, what are they called? Finite differences. I think that's the fancy term for it. We're going to look at the differences between our y values here. We're going to look for the first difference. And the first difference for linear equations would be congruent, or it would be equal. It would kind of be like the slope. Well, in this situation, it would be the slope. So we take the second one minus the first one. So 4.5 minus 2 is going to be 2.5. Then we're going to do 8 minus 4.5, and that gives me, I'm thinking 3.5, but let me make sure. Don't want to get it wrong. 8 minus 4.5, that gives me 3.5. All right, right there, by those two numbers being different, I'm thinking this guy's not going to be linear. Now I'm going to say 12.5 minus 8 is going to be 4.5. And then 18 minus 12.5 is going to be 5.5. All right, that right there, those are the finite differences, the first order differences. And if those were all the same number, then he would be linear, right? He would be degree 1, which is linear. Now what we can do is we can look at the second differences. The second difference is, if we subtract the second one from the first, we get 1, 1, and 1. These are all equal, making this guy quadratic. Now, it's hard to tell where his vertex would be from this, but if we wrote an equation, we would be able to tell. Now, with this being a quadratic, it makes writing the equation a whole lot harder. So there are some different ways that we can do that. For this one, though, I'd like us to use the calculator to do that, using the quadratic regression. So if you know how to do quadratic regression on the calculator, you can go ahead and do that. I'm not able to do that on my tablet here. So we're going to finish up saying that this guy is quadratic, and then I'll have to show you in class how to do the quadratic regression. So that is 27. Let's look at our next one. Where is that the end? Oh, that is the end. All right, well, that is 27 there, and that's the end of the Chapter 8 notes. So again, these differences here, just to talk about it a little bit more, we had these in order, right? -3, -2, -1, 0, 1. If we looked back up here, let me look at the problem we did earlier. This one right here. If I made a little t-chart here, and you don't have to do this, of course, and I wrote these in order, we'd have -2, -1, -1, 0, and then we jump over to 0, 1, 1, 2, and then 2, 3. If I subtract these, now it's kind of horizontal, it's a little bit different than what we were doing below, we'd have 0 minus -1 is 1, 1, 1, and 1. These are our first difference, which is also our slope. All right, so that's how that kind of connects together. Here, let me see if I can write that linear. All right, so that is section, what section was this? Was this number 8? No, number 6. Number 6. All right, big deal here, just coming back to it. We only did one problem, but this average rate of change, that's something that comes back in lots of things after this chapter. Okay, so make sure that we recognize that it is just, it is just the slope. All right, that's all.